Okay, so we record now. Hi, everyone. We'll continue with zero knowledge and move on to zero knowledge for a class of languages which commonly occur in cryptography. And but first, let me review some features of the zero knowledge proof for graph isomorphism that we saw last time. So recall what's the situation for that language. So you have a statement. The verifier has a statement. He doesn't know whether it's true. But suppose that it is in the language. So therefore, there is some there is a witness that shows that these two graphs are isomorphic. You can think of the witness as the pre-image of a one-way function that that takes a permutation and outputs a permuted graph of a fixed graph. So think of G1 as fixed and G2 an output of, why is it a one-way function? Because if graph isomorphism is hard, then given a sample, it is hard to find out what's the isomorphism behind that links these two graphs, right? If that was easy, then you would decide the graph isomorphism problem. Given two graphs, you would compute this pre-image and well, check that it's true. If you cannot compute it, then the reason would be that this is simply not, G2 is not in the range of this one-way function with G1 fixed. Okay, so what do we do with this to prove it in zero knowledge? We create the prover knowing this, this witness, or the way I want to now think of this, the pre-image of the one-way function, creates a new instance of the same one-way function. So completely independent argument, phi prime, and computes the one-way function on this fixed graph on this independent argument, that's h, and sends that h. Okay, so whereas the fixed one-way function image is G2, which is permutation phi applied to G1, in the proof system, the prover picks an independent argument phi prime and sends out the one-way function applied to phi prime. Okay, so permutation of this fixed graph using phi prime. And what the challenger does is with 1/2 probability, it asks for one of the following two things. It either asks the prover who have committed to this one-way permutation of the graph, this random one-time permutation. The verifier asks the prover, okay, please explain that you have created this H graph correctly, in an honest way. Simply reveal this one-time witness that you picked in this proof system and show that H is indeed a one-way function applied to this witness. Okay, so this is the challenge B equal 1, phi prime is phi prime, and the verifier just checks that indeed H is a phi prime of G1. The other case is using some homomorphic structure of this one-way function. So namely, the fact that if H is a one-way function starting from G1 applied to phi prime, this is the argument, and G2 is the same one-way function applied to phi, then there is a the same one-way function, so to speak, can be thought of as mapping from G2 to H using this modified witness. And with a probability 1/2, that's what the verifier asks for. Show me that the composition of these two witnesses, the fixed one and the one-time one, this quote-unquote one-way function has the property that if the permanent witness exists and the temporary one is also created correctly, then this composition will exist. Okay, so in the parlance of graph isomorphism, H is both a mapping of G1 and also a mapping of G2 using another permutation, right? A composition of these two. Why is it zero knowledge? Because in the B=1 case, what the verifiers showed is a random permutation unrelated to this one. And in the B=2 case, he also showed a random permutation unrelated by this one, because this composition of the two witnesses is like a one-time pad over the argument space, the domain of this, the argument domain of this one-way function. Why is it sound? So therefore, we can, this is zero knowledge, and by sequential composition of zero knowledge, it can be repeated any number of times, and it will not with fresh five primes, and will never reveal information, right? And we had the simulation argument that shows that. Why is it sound? Because if you can answer both of these directions, the fact that both of these witnesses exist implies existence of this permanent one by the same homomorphic property of the one-way function, which is underlying this whole thing. Note, a lot of NP problems, so any NP problem, well, okay, NP problem it doesn't have to be a one-way function. So only if the NP problem is hard. Moreover, it's hard on average, right? So given a random element from the range, from in the language, pre-computing the witness that shows that this is in the language is hard, right? So it's not going to be relevant for all problems in NP, but it will be relevant for many of them. In particular, and okay, and so what allows this zero knowledge proof? Well, existence of some one-way function, which is basically implied by if NP problem is hard on average. But more than that, it's a one-way function that has some homomorphic properties, which allow the fact to compose these two, the permanent and the one-time witness, in some, well, so that to link the permanent one-way function image and the one-time one-way function image. And that structure is not part of any NP problem. In fact, for 3-SAT, for NP hard problems, we don't know. So why do we start with graph isomorphism? Because we see this homomorphism that allows this move. And that is not, we can always do this with like any NP problem. This is a, this is an instance of, this is some public parameters. This is an instance of the problem. This is the, so think of 3-SAT formula. This is an assignment. Of course, we can create a new random assignment and create a new formula. But what is this? Is there some way of mixing the two assignments and relating these two formulas? Many problems do not have this structure, but cryptographic ones do very often. And so that's what we are going to speak not all, but some. So that's what we'll speak about next. Okay. So zero knowledge. For languages implied by homomorphic. No, this is not the best pen, I think. By homomorphic one-way functions. And these are often called sigma protocols. So these will be zero-knowledge proofs with certain special protocol properties. So special honest verifier zero-knowledge proofs. We don't know this term yet, but that is a very natural restriction really on zero-knowledge proofs. And we'll explain what that means. And of course, we'll see what that means. Okay, so take a homomorphic one-way function, function. F that takes some domain into some range, and it is well, so it is one-way function given a random element in the range. It's hard to compute the preimage, and it is homomorphic in the following. In the following sense, D and R are both groups. And for every x1, x2 in the domain of the one-way function, if I compute the one-way function on x1 and I use a group operation from the range and apply it to the image of the one-way function on point x2, this is the same as applying the one-way function on the argument that results from combining these two arguments using the operation, the group operation in the domain. Okay, so examples, right, are needed. Let R be a group generated by generator G, a cyclic group of, let's say, prime order Q. Okay, so, and the domain is the Q. Okay, you know, the integer residue mod Q. Okay, and let f of x be g to the x. Okay, so this is so of course, so this is an exponentiation in group G. So there's two basic instantiations of this. We know G generates. So first example is G generates a Q order subgroup of ZP star. Q divides P minus 1, and G to the X really stands for G to the X mod P, right? So G is just some, P is a prime, Q is a divisor of P minus 1, and G is an element of order Q, meaning, and the exponentiation operation is a modular exponentiation mod P, right? 2, G is a point not equal to a unity on an elliptic curve of order Q, of prime order Q, and G to the X is really is defined as multiplication of point G. So this is where this is so in other words, point plus point plus point X times, and these are point addition over the elliptic curve. Okay, so the group operation in elliptic curve is called addition, right? And but the same discrete logarithm issue holds that, right? So it's an additive notation for a group operation. Here's a multiplicative notation. We'll stick with multiplicative notation throughout, but it maps to elliptic curve cryptography like so. Look, it's homomorphic. F is homomorphic for, you know, homomorphic. The F of x1 plus x2 mod q. So this is the group operation in the domain, in the domain group, right? Which is CQ, is equal to G to x1 plus x2, and this is of course G to x1 times G to the x2. So this is f of x1 times f of x2, right? And this is the group operation in G, in the range, which is a group generated by G, right? So this is a group multiplication in the target group, right? Like either this Q-order subgroup or an elliptic curve, and it works. Another flagship homomorphic permutation is the RSA one-way function. So RSA permutation, the range is the same as the domain, and is Zn star for n and RSA modulus. And the function is x to the e mod n. Okay. And of course, f x1 times x2, so this is the mod n multiplication, is the same as, well, so that's x1, x2 to the e. So this is x1 to the e times x2 to the e. So that's x1 times fx2. And this is also the mod n operation, right? So in this case, the domain and the range are the same multiplicative groups, mod n. So the domain operation and the range operation are the same. They're the same two groups. Okay, so here technically NE must be pre-generated at random from the RSA key generation on security parameter distribution. So it's not a one-way function in the same sense of here that there are public parameters that define the function, and it is the function must be, the parameters must be randomly generated, or otherwise it's not true that it's a one-way function for every NE. But other than that, it fits this schema. Okay. Cool. Zero knowledge proofs for language defined by this function f as follows. It's a language of all elements in the range such that there exists an x in the domain such that y is f of x. And if you need, you can add whatever parameters that define f. This can the parameters that define f can be part of the statement. Okay, so the full statement is not just elements from the range, but the parameters that define the function and elements in the range. And it's in the language if there is a preimage that explains this y as an element in the range. Now, this language is trivial for if the function is this one, because everything in Zn star is an if root of something else. Likewise, for this one-way function, every group element, G is a generator of the group. So every element in the group is generated by G, and therefore every element can be explained as G to something. But LF is trivial for above two examples. It's trivial because LF is simply the range for both. So decision is immediate. You're getting an argument and you say it is in the language without checking anything. But here's an example of something for which a one-way permutation like this, which is no longer a trivial thing. So the elements from the range of the one-way function form a proper subset of the range, and deciding whether an element in the subset is hard. So let's take another example. F takes a ZQ and maps, gives you a pair of elements in the group generated by G. And F by G and H elements of group G. And the function is like this. F of x is a pair G to the x, H to the x. Now, given G, A, H, Y, and Z, to decide if there exists an x such that YZ is G to the x, H to the x, is a decisional the Diffie-Hellman problem if H is random in the group. So this is and X is random in ZQ. So, okay, sorry. What I said here is a little bit nonsensical because the way I generate these, they are guaranteed to be in this language, right? So the proper thing is decision must be between GHYZ formed into S G G to the G to the, let's say, R G to the X, and if H is G to the R, then Z guy is G to the Rx for random Rx versus they are just taken at random from the group. Okay. So this is a decisional Diffie-Hellman problem. In other words, if I give you a random point, either a random element in this range, which is this. So first of all, if I decide this parameter, I pick it at random, which is, okay, just similar as in the RSA case. The parameters must be chosen from some distribution. I can make H explicitly part of this problem as well, but it's just easier to push it as a parameter because I want it to be fixed throughout. So this parameter is chosen at random, and then and if the parameter is chosen at random, then deciding between a randomly sampled point in this range, which is this case, and a point in the range which is belongs to the image of the one-way function f, parameterized by these, which is this case. That's exactly the decisional Diffie-Hellman problem, right? So, I mean, not in every group, the decisional Diffie-Hellman problem is hard, but it is posited on many prime order groups, and you can find instantiations, right, where the problem appears hard, and indeed it is a basis of public key crypto systems. Okay, so now it is non-trivial. The language LF of values y in this cross products of the group such that the language F is basically parameterized by G and H, and I want to call these images Y a pair YZ, such that there exists an X such that YZ is GX HX. Then this language is no longer trivial to decide on randomly sampled points. Okay, but F is homomorphic, just like the exponentiation function So f of x1 times f of x2, which is defined as, okay, so what's f of x1? Is gx1 comma h of x1. What's f of x2? It's g of x2 comma h of x2. And this is pairwise multiplication. So I can think of the cross products of these two groups as a group, where the group operation on pairs is just a group operation, pairwise group operation, right? So this is g x1 plus x2, comma h x1 plus x2, which is f of x1 plus x2. Look at the applications that was given as one of the examples of what kind of thing we would like to prove in zero knowledge. F is think of L as the language of equality of plain text. So it's a language of, I have, let's say, two public keys and two ciphertexts, such that there exists a message, randomness 1, randomness 2, such that C1 is an encryption under public key 1 of message 1 using randomness of the message using randomness 1. And C2 is an encryption under PK2 of the same message using R2. So the important thing is that these two messages are same. Okay, okay, let E be El Kamal, textbook El Kamal. How does it go? Public key is y, which is g to the x for random x in ZQ. So that's the El Kamal. The El Kamal is Diffie-Hellman, but viewed as a public key encryption. And the encryption under a public key y of a message m and a randomness r, where the randomness is, this is random in ZQ, and the message is an element of the group generated by G, is a pair G to the R, Y to the R times the message, right? That's the El Kamal encryption. Okay, so let's see what this language is. So, so in this case, so the language of equation of equal of El Kamal encryption plain text is, so let G be the public parameter, right, of this group. So I guess it's parameterized by G. It's two public keys. So the public keys are Y1 and Y2. And I guess let's call this, okay, let's call this ciphertext. So if this is called C, then let's call it E comma F, okay? Because it's a pair. So the first ciphertext is E1 F1. The second ciphertext is E2 F2. And that's the statement in the language, such that there exists an M in the group and R1, R2 in ZQ, such that And okay, such that what equations do I have? E1 is G to R1, E2 is G to R2, and F1 is Y to R1 times M, F2 is Y to R2 times M. Now, I can equivalently, sorry for the ugliness of these brackets, I can take the system of equations is equivalent to the following statement, that there exist just R1 and R2 in the Q, such that E1, E2, and F1 divided by F2 are equal to G to R1, G to R2, and Y to R1 minus R2. Okay, because here I said that there must exist some M that fits these equations. Well, if I divide F1 and F2, and it is indeed the same M, then the division must be explained as Y to the difference between these two exponents. In fact, I can, and this is equivalent to, which is equivalent to existence of some value delta in the Q, such that E1 divided by E2 and F1 divided by F2 are equal to G to the delta, Y to the delta. This equation is equivalent to that one. Okay, well, this one clearly implies this one, but also this one implies existence of an M that once you multiply, divide F1 by M and divide F2 of M, you're gonna get Y to R1 and Y to R2. But this, well, this clearly implies this one, but this one implies that one, right? Just pick any R2, and this will define R1 in relation to the delta and R2. This is, so in other words, which holds if and only if E1, E2, and F1 divided by F2 belonged to this LF G. Oh, no. Oh, sorry. You know what? I guess nobody noticed that here I have suddenly from two public keys, I created a single public key here by just overlooking. You know, in order to not to mess too much, I mean, it will extend to this. Let me just force this into a language of equal plain text for under the same public key. Okay, because I just, you know, instantiated this way without meaning to. Let's kick out the second public key and make these two public keys equal. Okay, so the public keys are also equal. Okay, so the language is of two ciphertexts that encrypt the same message under the same key. Okay, I want you to prove that you encrypted the same thing as before. Yeah, okay, maybe it's not so obvious why. Perhaps I have an encryption of your password and I want you to re-encrypt it to prove that it is the same one as you encrypted previously, that you still know it, so to speak. So I ask you to encrypt the same password and prove that whatever you're encrypting now is the same thing that you encrypted before. Okay? So this is in the G in this language here. Okay. Okay, so let's see how to create a zero knowledge proof for this type of homomorphic, for a language defined by the one homomorphic one-way function in this way. Right. So the language of images of a one-way function, and this method will apply to, for example, this case, right? Okay. So so again, F is a homomorphic one-way function, and the language associated with it is of elements in the function range such for which there exists a preimage. Okay, so let the verifier has an element in the range. So now this is the statement in language LF. So this is, not, the notation is a little bit clashy. Often in ZK proofs, statement is denoted X. Okay, but here I'm going to denote the statement as a Y. The prover has the statement, but he also has the witness. So this is a witness for that Y is in this language, and this is often witness is denoted W. Okay, we use this notation to introduce zero knowledge proofs. X was the statement and W was the witness. Okay, so what does the prover do? Well, something not dissimilar from what let's take the graph isomorphism as a kind of a blueprint and try to use that intuition. So the prover is going to pick a new random witness from the domain of the function, and he will give to the verifier image of the same function on this random point. The verifier will ask will challenge the prover with a bit, like before. And the verifier will respond with the value Z, which is either equal to this one-time challenge, this one-time witness, if the bit is 1, or the combination of the two witnesses, the permanent and the one-time, using the homomorphism over the domain group of this one-way function. So this is operation in the domain applied to the permanent and the one-time witness if in the other case if the challenge is true. What does the verifier do? He checks accept if a function applied to Z is equal to well, y prime if the bit is 1. And in this case, what should it be equal to? Well, y prime, or it should be y. The group operation of the target group applied to the presumed one-way function of x, which was y, and the presumed one-way function of x prime, which was y prime. Okay. So right here is the role of this this composition of these two permutations. The composition of the two permutations play in the Greif isomorphism proof. You have using explicitly a group structure of the domain of this one-way function for that. Okay, so completeness of course holds. Yes, if everybody runs on the proper stuff. So the assumption here was that, f of x is equal to y, right? Holds. So verifier always accepts if y is indeed f of x, and if the prover follows the protocol. Let's see soundness. So if y is not in the image of f, okay, i.e. There is no x such that y is f of x. So in the example of that we have, that we had here, the verifier has this tuple, and it is not true that the yz is g to the x, h to the x for any x. Okay. Then I claim that the probability that the verifier accepts is at most 1/2, because for every y prime, there can either exist z such that y prime is f of z. It's so for every y prime that the cheating prover is going to send, there will either exist a response for b equal 1 case or b equal 2, or also none, but at least these two can exist, but they cannot exist at the same time. So there can exist a z which y prime is f of z, or there can exist, let's call it z prime, such that y times y prime is f of z prime. So that's checked in the B. So if there exists such a z, then the cheating prover can satisfy B equal 1 challenge. If there exists this C prime that satisfies this relation, then the prover can satisfy B equal 2 challenge. But if both Z and Z prime exist, then what do we know from the homomorphism of the function? Then y times y prime divided by, multiplied by the inverse of y prime, and it's a group, so it has, everything has an inverse. You know, think of, in this case, division, right? Well, this must be equal to f of z times f of, well, minus z prime. So this is the inverse. So this is the inverse in the range group, and this is inverse in the domain group. I'm using assume it's additive. So indeed, in this exponentiation example, my domain group is additive, is ZQ, right? So inverting multiplicative inverse of g to the x is g to the minus x. So multiplicative inverse of in the target group corresponds to additive inverse in the domain group.
Professor?
Yes.
Could you move the page a bit?
Oh, yeah. Oh, sorry. Oh, sorry. Okay, thank you. So by additive homomorphism, this is the same as f of z minus z prime. So this would be, and why did I do this? So that to cancel in the target group the y prime, this is y, right? So this, so this is, so this would imply that there is an x, namely z minus z prime, such that f of x is y. Right? So see, for example, the exponentiation example. Yes, if you are bothered by the abstract notation here, then well, okay, but here I denote, so if, well, I have to change notation. ZV is g to the x, h to the x. So that's a y. Y prime would be z prime v prime, would be g x prime, h x prime. That's what the prover. So if the verifier statement is a pair, and the verifier wants to know, are they in the same, are they a so-called decisional Diffie-Hellman tuple? Do they have a common discrete logarithm from some fixed basis, right? Which we have seen, this language of equal plain text, of re-encrypting the same plain text, it immediately reduces to this case, for the case of textbook Tel-Gamal. Okay, then what would the prover do? He would pick a x prime and create random point in the same range, z prime v prime, g to x prime, h to x prime. And let's say he can reply with the z. Okay, unfortunately, there's the same z as in here. Okay. Well, I guess I will call it w, and I will call it w prime. So let's say if there exists z such that y prime is g to the z, h to the z, right? Which is the B1 case. This response is accepted only if this holds. If the response is the preimage of this one-way function corresponding to that maps to point y prime that the prover sent at first. And if there exists a z prime such that two of them multiplied, y times y prime, is g z prime h z prime, then what does this equation imply? It implies that the product, this is w prime v prime, right? Because y prime is w prime v prime. Y is wv. This guy is y prime is w prime v prime. So this is also equal to, this is equal to g z prime h z prime. Now I divide this equation. This equation by this equation, and what do they imply together by cross dividing, right? If I divide this stuff by, then I lose w prime v prime, and all I get is wv on the left hand side. And what do I get on the right hand side? I get this divided by gz hz. This is clearly equal to g z prime minus z, and h z prime minus z. Oh, sorry. This was the witness here was called z prime, and the witness to y prime was called z. So this is z prime minus z. Okay, which indeed it is here. Yes, so this is my x, which shows that my y was indeed in the language. Okay, so all of this is this concrete example where you see the same math concretely, right? Are you guys following?
Yeah.
Okay. Okay.
I think the previous one was easier, the abstract one.
Oh, okay. But I mean, you know, you can look at this later, right? Like, I mean, it's the same. It's the same thing.
Yeah, just more.
Okay. But I mean, it's cleaner in this version. So if the underlying thing has a 1/2 soundness, so this implies that by same argument as in the graph isomorphism case, a sequential repetition gives you a probability of V accepts on Y not in the language, on Y not in the language gets down to 1/2 to the security parameter, right? Okay, but crucially now, what about zero knowledge? Okay, let's bring the proof system into the picture, right? And see, well, how did the how did the simulation go? Simulator knows only the statement, doesn't know the witness, doesn't know the pre-image. How did the simulation go in the graph isomorphism case? Well, same blueprint as in graph isomorphism case. The simulator bet on the guess the bit B, that verifier. So this simulation is for arbitrary cheating verifier, as it should be. Right, let's call him V star. Let's guess bit B that verifier V star will output, and let's call it B prime, this guess of bit B. So B prime is chosen at random. It's either 1 or 2. Okay, now if you guess this bit B, what did the graph isomorphism simulator do? In the graph isomorphism case, we started simulation from the bottom up. So we use the fact that phi prime, whether the challenge bit is 1 or it's 2, the phi prime is always a random permutation. Well, it's the same here. Z in the B equal 1 case is explicitly a random point in the domain that is independent of X. But in the B equal 2 case, it is an independent point as well. Because if G is a group, then NX prime is randomly sampled from the group. Then a group operation is a one-time pad because inverses exist, right? So an operation of taking an X and operating and using a group operation by a random point is a random permutation in the group. X just went to a completely random point, right? Because for any target point, there exists a unique X prime, which maps X to that random point. So it is a one-time pad in the group, just like masking a permanent permutation by a random one was a one-time pad encryption in the space of permutations, right? Information theoretically, it hides this permutation and creates a randomly sampled one, which is independent of phi. Likewise, Z in this case is also independent of X. So the simulator will therefore start from the bottom, just like the graph isomorphism simulator, the simulator for the zero knowledge proof for graph isomorphism. So it picks Z at random in the domain. Okay. And then it fixes the message Y prime so to fit the verification equation, namely Y prime must be either FZ if bit is 1, or Y prime is computed as FZ and a group operation applied to, well, the inverse of Y if B is 2, right? Because if that's how I form my Y prime, then it's gonna fit this case. I will send that to the verifier, and if he asks for B2, I will surrender the Z, and now check that f of Z is indeed this, because Y prime is this, so Y inverse and Y are going to cancel, and well, I guess, yeah, homomorphic functions. Okay, I implicitly I assume that it's what's that property called of the groups where x times y and y times x is the same thing. Okay, I forgot. But I assume that structure of the group. Did somebody remember the term? No.
Commutative?
Commutative, yeah. Thank you. The range group commutative. And maybe that follows from homomorphism, but no, maybe not. Okay. Well, they were commutative.
No, it doesn't.
Okay. Well, anyway, I didn't even have to do, all I have to do is to invert these, but it's easier for me to write that than to erase. And then test if, okay, sorry, we forgot the first part is, so the first step, first step, fix random tape W of V star. Okay, so make the verifier a deterministic algorithm by just picking a random tape for him. So and now test if V star on input Y and message Y prime, given that his random tape is this W, or I think it was omega, is equal to B prime. If yes, output Y prime and Z as the transcript of this instance of zero knowledge proof. In other words, the message Y prime, and then given the response B prime, the final message Z. If no, recurs. Okay, so that recurs to this step. So don't change the randomness of the verifier. Just pick a new bit and start anew. And by same argument as in the GI case, the probability this fails in SECPAR attempts, yes, is less than 2 to the minus order SECPAR. So negligible. And the zero knowledge argument for this is identical as in the case of graph isomorphism, right? So first we, well, the random coins are picked correctly. And then first we argue that this is indeed the case, that the failure is negligible. And then we condition on this bit being guessed correctly. And then look at the distribution of y prime z condition upon this, that the guess was correct. Because in one of these executions, if this security parameter number of executions, it is guaranteed to be correct except for this negligible probability. And each of these executions, by the way, just by looking at this, are independent. Okay, so it's all freshly sampled, right? And you know, if you so the only reason why I insist on taking this randomness of the verifier text is because I want to reuse it for sequentially number of times, because eventually I want to have sequential number of these executions, right? To drive the soundness error to be negligible. So condition upon the verifier response to be the same as the simulator's guess, the distribution of y prime z output at the simulator and the distribution that in that case the verifier would see coming from the honest prover are identical, because for regardless of the case of b prime this is, so whether it's a 1 or 2, condition upon that bit being correctly guessed by the simulator, z is uniformly distributed in the simulation and it is uniformly distributed in execution. And y prime is a deterministic function of z, because y prime, well, in both cases, right? Because, and the function is exactly that one. So in the case of B1, y prime is just f of z. In the case of B2, y prime is f of z shifted by the inverse of y, the statement. Okay, so it's exactly the same argument. Let's see how much time I have. Okay, so I should be finishing here, but let me just do so we're running soon out of time. So unfortunately, I will have to postpone this. But here is the main point. So this is okay. Zero knowledge exists for this language, for any such language, and it's formed in very similar way to the graph isomorphism zero knowledge proof. They exist, but they still, in order to have realistic soundness, right, negligible soundness error, I need to repeat this basic proof 100 times, okay, or whatever the security parameter I want. I want to achieve. Each of these obviously costs 100 rounds, right? Because I guess I can piggybacking answering the previous case with sending the new y prime, but it will take 100 of these interactions. The cost, if this is a public key kind of permutation, one-way function, right? Like exponentiation. Well, this is 100 exponentiations. So when I encrypt a password, and that cost me for Elgamal 2 exponentiations. And now I want to prove that this encryption is the same as the previous one. Well, that will cost me 200 exponentiations. So 200 rounds, where at each point I do 2, and the verifier also does 2, right? Because the expensive part is that this is a homomorphic one-way function. We get examples of that from public key cryptography, right? And the application I wanted to do is directly coming from public key cryptography, right? So that's not great. However, if I consider only honest verifiers, so if I consider, this, you know, have to do order of SecPar repetitions. So repetitions. So not great security, not great for efficiency. And parallel composition fails. It fails for the same reason as before, for the same reason. So if I consider, but if I consider only honest verifiers, then I can use the homomorphic structure of F to have long challenges. So no longer just a bit B, which was either, you know, the verifier was here in all these systems, just choosing, give me either one of these explanations, explain y prime as the permutation, as the one-way function, or explain combination of y and y prime as the one-way function. Using homomorphic structure of these one-way functions, I can explain a random linear combination of y and y prime. And that would give us a negligible soundness error for just one execution. Okay, so a single execution of a system very similar to this one, and you get negligible soundness error instead of just 1/2. But you don't get general zero knowledge. You only get zero knowledge against honest verifiers. And then we'll use tricks to compile from honest verifier zero knowledge to full zero knowledge at reasonable costs. Okay, so that's just the plan for what we want to do, and so I will see you on Thursday. But let me know if you have questions.
So this move from honest verifiers to full zero knowledge, will it work always or just in a specific case?
So it will work for, I guess, okay, very good. It will work for special HVCK. So we'll see exactly what the special HVCK means. Right now, it will not work for every homomorphic system. Like, for example, but once these groups are prime order groups, then it will. Then they will hit they will have these special properties that are required for the compilations. There is many of these compiler results extending the range of these proof systems. The prime order groups are the simplest ones. If you want to, but obviously people wanted to extend to RSA cryptosystem and now to lattices. We'll first just assume prime order groups because they're the simplest case.
Okay, thank you.
All right. Thank you, and see you Thursday.